Hello and welcome to my channel again. So today's video is a continuation of the last video I've done about the accidental degeneracy of the hydrogen atom. And on the previous video we have proved something called Rungi Lenz vector, and we have seen that it is a conserved quantity due to the dynamical symmetry of the system. And in today's video we will also try to prove that if we add a slight perturbation to the existing potential, like this Coulombic nature we have seen between the nucleus and the electron of the hydrogen atom, it becomes a perturbed system and the accidental degeneracy is lost. Okay, so we can say the symmetry is broken some kind. Okay, so why is that, we will see, and after that we will explain what is the SO4 symmetry, why is it SO4 symmetry. We will not prove that, but we will just touch the particular topic, that is SO4, and for the bound state particularly it is SO4. For scattering state it becomes SO1, 3, which is the Lorentz group or the Lorentz symmetry. Now after that we will prove a certain quantity. Now you will ask that what is the necessity of proving that quantity, and today's video I won't be able to cover two like derivations of that particular quantities, because those are very long. But in exams I have seen the university asked this type of questions, at least in our university they ask, and it is very hard for a person who is not acquainted with the process or the way it should be done. Okay, I will try to make it short and as much compact I can, but I will explain certain methods so any of you who are watching on the other side won't face any problem. Okay, so just let me rub my board and get started with the video. Okay, so I have erased the board, and I would like to deeply apologize for the previous video because I had some serious scaling issues, and as you guys can understand that I cannot see myself on the phone screen, and on the other side I don't have a mirror so I can see my phone screen on the reflection. So I really assume that there's some kind of a boundary, I have some kind of an idea, but previous day I actually changed my room setup a little bit due to some reason, so I haven't got the idea, like the camera position has changed. So I'm very sorry about the scaling issues, and if you guys are having any type of problems regarding the first video, I will give that link on the tab button if you're new and seeing this video first. Now do let me know, then I will delete that video and re-upload it again with the proper scaling and proper explanations. Okay, but I don't think I've seen the video after upload. I don't think that it is much of an issue, because some kind of derivatives were just involved on that part where the frame got cut. So I hope it's okay, but if it's not, then do let me know in the comments. Okay, fine, thank you. Now I will just start with the first part of our video's agenda, that I have claimed that let us consider a part of Hamiltonian which is being added to the hydrogen atom Hamiltonian, and let us consider that it is a bound state potential. So I will consider that as epsilon by r square with a minus sign, because it is a central bound system. Now if I add this h prime, which is looking something like this, where epsilon is obviously greater than 0, okay, which is trivial, but I'll let to mention it. Now if we add this term to the hydrogen atom potential, now our energy eigenvalue En is no longer that 1 by n square and some constant, that is 2 n naught e square h cut square, I guess. Okay, I'm not very sure about the constant, e square h cut square by 2 n naught, I guess. Okay, it is not just this value, because now I have to consider the average value of the system. And when I use the first order perturbation theory, I will just calculate the E prime, okay, which is basically the average of the perturbed Hamiltonian, which basically represents minus epsilon average of 1 by r square. I mean, now you guys can understand why I'm so much concerned about this, because this 1 by r squared is basically, we know that 1 but n cube n naught square L plus half. Now here is the twist, or here is the story, that see, our energy correction comes to be L dependent. Now we don't have that accidental degeneracy left, because our energy expression with some I can say the total energy E total will be E prime plus E naught, which is our unperturbed energy, this, and added with this E prime. So now E prime got the dependence of L and the L degeneracy is lifted. Okay, the degeneracy in L is lifted. So due to that reason, I am always saying that the accidental degeneracy, okay, the accidental degeneracy is highly sensitive upon the potential. So if you take a potential which is slightly non-Coulombic, I am not replacing the entire potential. You need to understand that the actual Hamiltonian, which is basically that p square by 2m minus e square z square by r, is much greater than this part of term. Okay, I am considered epsilon greater than 0, but it is a very small quantity. Okay, now you have to understand that the strength of this H prime is very low. Okay, that means the epsilon is very small. It's positive, but it's small. So the contribution of this 1 by r square will not be very much high. Okay, but you cannot take L equals to 0. You can change the L. The energy is dependent upon the L. Now E just not N, but here I will have a L also. E N L. So the degeneracy is lifted. Okay, you cannot have anything any other than Coulombic nature of the potential. Okay, you are not allowed to have that thing. Okay, I hope you have got the idea here. I will not put any cut here. I am just erasing. It will take some seconds. Now see, I have said multiple times that I will tell you guys something which is called the SO4 Lie group and SO4 Lie algebra. Now what's that thing? Now on the previous video I was talking about the SO3 algebra and all, but that part got into the frame issue. So I'm just writing here again that ML is the quantum number associated with SO3, which is basically the rotational symmetry, right? Rotational symmetry of the potential. The potential is central and it is Coulombic, so it has a rotational symmetry in it. Now, if we take Lz L square, now these are the operators that belongs to SO3, right? In terms of the generator, they exist. Now, our problem was that we don't have such a symmetry for L. How can I algebraically or group theoretically deal with the degeneracy which lies in the L? Because it was a dynamical symmetry, it's not a space-time symmetry. SO3 was a space-time transformation related symmetry. Here we have the dynamical, which is basically manifestation of the equation of motion. Now, we will associate and SO4 Lie algebra. Okay, that was SO3 Lie algebra, Lz and L related to, and this is associated to the SO4 Lie algebra. Now what is SO4? SO4 means it is not a closed Lie algebra. Now you guys have seen, I will assume that you already know some kind of a group theory. Now in group theory you already know that for a group to be forming Lie algebra, Lie group, you should follow some certain properties in which it is very important that the group is closed, because you cannot claim something to be a group if it is not closed. So on the first place, when I studied SO4, I was very confused about the fact that when something is not closed on the first place, how can it be a group? Okay, so now these are special kind of groups we are allowing. So you will see that our Rungi-Lenz vector was defined like this. Okay, I some kind of a fancy kind of an R I did. So okay, let me change my ink here. We already know that due to SO3 and Okay, SO3 will always be a subgroup of SO4 because definitely SO4 is a bigger symmetry, so SO3 will lie inside it. These are angular momentum operators. We know that I will ignore that IH cut part. Okay, let me write it. Epsilon I J K L K. Okay, these are constant, so you can ignore them to understand the actual symmetry part. These are the scaling factors. Now, if you write Rj, according to closed Lie algebra condition, you expect that you should get some R dependent quantity here. Okay, but here is the twist. As it is a non-closed algebra, you will get 2i cut by m with a minus sign, then the Hamiltonian of the system. Okay, Hamiltonian of the system, then epsilon ij k, not lk, sorry, not rk, but lk. So you are seeing the thing that we are starting from R and we are reaching at L, so it is not closed. Okay, and if you take RILJ, you will end up IH cut epsilon IJK RK. Okay, so if you see, this is closed, but these two have some kind of a problem here. Okay, you can claim that yes, this is obviously an SO3, you know that, but this is not closed. Same for this. Then what's happening here? So we will claim that this entire thing is closed. Okay, not this separately, not this, but this entire thing will represent the SO4. This entire thing is SO4. I hope you are getting some kind of an idea here. Now, here we are talking about bound state. Okay, I will not go into that much detail because it is related to some kind of a quantum field theory part, but I will give you a brief introduction what I am talking about. I don't know if the board is visible. I will just gonna stick to my door, and let me give you an idea that here we have taken the energy to be negative. I know this is my boundary. So E is less than 0 here, okay, which represents it is a bound state. And the operator associated with this energy will contain this negative energy inside a root. Okay, I'm not going into details, I'm just telling you the dependence. So this is what is representing SO4. Now if we take the E is greater than 0, these are not important for exam, these are just for knowledge. Okay, this SO4 and this part. If you take the E greater than 0, then it is a scattering state. Then it's a scattering state, which means that the dependence of the energy is now positive, okay, of that operator, which means it is now not SO4 but SO1, 3. And SO1, 3, if you know then it's good, but if you don't know, it is basically Lorentz group. I may have written the spelling wrong because one have T and another one don't. I don't remember it, but it is called the Lorentz group, SO1, 3. So SO4 and SO1, 3 are related when you are talking about hydrogen atom, and you can switch back and forth by scattering state and the bound state. Okay, I hope you have understood up to now. If you have any doubt, please write me in the comments, because you know, these things are very much like elaborated topic and I have to sum up in a very small and understandable manner. So I'm definitely missing some points, losing some data to make it understandable. So if you have any kind of problem, please do let me know. Now I'll just erase the board and go with the derivation I'm talking about. Okay, so I have erased the board, and the quantity or the thing we're going to prove is that Rungi Lenz vector taken dot product with angular momentum vector L will be 0. Now here I want to tell something that as these are quantum operators, you cannot say that r dot L equals to 0 basically represents L dot r 0. So I will do the r dot L. I will give you as your homework, not as your homework, you guys are not kids, but as your practice that try the L dot r equals to 0, try to prove that. Okay, now it is frequently asked on examinations, so I will just do it. I will assume that you guys know Levi-Civita symbol uses pretty much from now, because otherwise it will be very difficult for me to do this whole thing. Okay, because it is already very lengthy thing to do, and the second thing I said will be done the next day, but I have to prove that r square is some quantity. Okay, that will take me a very long much time. I will just start. Okay, I'm writing normal r, please don't get confused. This r and these are the same thing. I cannot write that much curl every time, it will take lot of time. So just r dot l. Okay, and I will just break it into index, which means that ri li. Okay, now we know that ri can be written as p cross li minus l cross p I by 2m minus kr by r with the I. Okay, now I will take the dot product or the multiply with li, which will end 1 by 2m p cross li minus l cross pi. Everything here is a quantum operator. Okay, so everything has an operator status here. These are not unit vectors, so they are always non-commuting. You cannot say I can just swap them, I can write 2ab type of thing in the whole square format. Okay, you cannot do that. So ab and b are not in general same. Under different circumstances it can, but in general not. So that's why it is lengthy. I li. Okay, we will deal with the second term first, which means this term, which is basically k by r ri li. Okay, now li basically can be written as r cross p, you know. So mod r epsilon I j k ri rj pk. All of them has operator status. Now position vector commute with each other. Okay, so this will basically give us r cross r kth component. Now r cross r I can write 0 because these are the position vectors. So this is 0. Our second term is 0. So our entire term is now reduced. I will not give the vector sign because I am dealing with components here. So this is equals to 1 by 2m p cross li minus l cross p I li. Okay, now I have to break those. Epsilon I j k p j l k li minus epsilon I j k l j p k l j p k li. Okay, now you can see epsilon I j k can be taken as common. So 1 by 2m epsilon I j k Okay. Lj, Pk, Li, I can swap them. I'm here expecting to write it as a commutation. Okay, so I will just add and subtract term to make it look like a commutator. Okay, so commutation means I have to put a minus. So Li, Lj. Now I can take the epsilon ijk here because this is just a number, so it has nothing to do with commuting with pj and all. This is a number. I can take this inside, and this will give me pj. If I exchange the I and k index here, because these are cyclic, okay, I can do that. So kij it will be not pj, sorry, ki. Now if I shift the j from here, this will again be a cyclic process, so it will be jki. Okay, for the cyclic terms there will be no minus sign, so now it's ki minus epsilon I jk li pk lj pk li lj pk li lj pk. I'm missing something, I guess. lj pk li lj li pk, sorry, lj li pk, right, lj li pk. So now I can take the lj common and write is as a commutation, that is pk comma li. Okay, and plus li lj pk. Okay, so I hope you guys can see this, it is visible. So this is basically the cross product of L and L. Now in the case of position, I said they commute, but the L's in general do not commute. Okay, Li Lj is not equals to Lj Li. It is I epsilon ijk Lk. So L cross L is not 0, but it is L. I h cut L. So I will just write it as L cross L with a J component. Okay, so this is if it is visible, I don't know, I'm just giving you a hint. Okay, that in vector form L cross L is not 0 quantum mechanically. I'm putting the operator status here, I h cut L. Okay, do remember that the L's don't commute in general in quantum mechanics. So it is pj, and this will give you L cross L, which is basically lj. Now minus epsilon ijk, you can take that inside, epsilon ijk, and lj. Now pk and li will give you minus ih cut p, let's say epsilon ki L PL, okay, and plus Li Lj. Oh no, the epsilon will be there. Sorry, epsilon Ijk Li Lj Pk. Now this will give you again the Lk. So I'm just writing it as Lk, okay, by erasing this. Sorry, I made a mistake here, okay. This is not just IH cut, this is minus IH cut Lk. I've done a mistake. This corrected. Sorry, this will be minus. Okay. And you guys can keep that IH cut by IH cut by 2m. Okay. Now I have here minus Pj Lj minus epsilon Ijk epsilon Kil Lj PL minus IH cut taken, so Lk Pk. Okay. Now if you see, sorry, this is plus. If you see, this will give us just 2 Kronecker delta. Pj Lj plus 2 Kronecker delta. I have Ki, so it is JL basically. JL Lj PL minus Lk. Okay. This is the property of Kronecker delta contraction. Okay. So minus Pj Lj plus 2 Lj Pj minus Lj Pj. Okay, I have changed the index. If this is a summing index, I can change it. So here I have a minus, here I have 2. So I will erase it and I will give it plus. So this finally boils down to IH cut by 2m Lj Pj minus Pj Lj. Okay, I guess you guys are convinced and do agree with me. Now let me write IH cut by 2m delta Ij, then Li Pj minus Pj Li. Yes. Okay. If you apply the Kronecker delta, this will give you the same thing. I'm just taking Kronecker delta out. Okay, I think I have missed. Oh no. Okay, fine. Sorry. And this is the cross product I can write. IH cut 2m, then delta Ij, then epsilon Ijk let me look at it. L cross P. That means it will give us epsilon Ijk Pk. Okay, no, sorry, this is wrong. Sorry. This is IH cut by 2m delta Ij. Now this is basically Lp minus Pl whole the jth component it was. So I took that Kronecker Ij and written as the cross product. So it will give us basically epsilon Ijk, the commutation of the L and P. From there I can write epsilon Ijk Pk. Okay. Now see, here is a twist. The twist is that Kronecker delta will set two index of the epsilon ijk to same. That means epsilon jjk or epsilon iik, which means that this part will essentially go to 0, and which proves our point that indeed the Rungi-Lenz vector taken dot product with the angular momentum vector will be 0. Okay, so we have proved our point that indeed the Rungi-Lenz vector taken dot product with L is 0, and on the next video I will try to prove that the mod of this R square will give you some kind of a Hamiltonian dependent quantity. Okay, I hope you have understood the video, and I will sum it up today. If you have any kind of doubt, please do let me know in the comment section. If the video is helpful for you, do like it and share it with your friends if you want, and don't if you don't want to, but whatever, I don't care. Now here is the thing I want to sum up. Okay, like the accidental degeneracy, why it is I have done it, how it is created I have done it, and after that if we see the potential is getting perturbed, then the accelerated degeneracy is lost, we have done it. After that I have proved certain quantity. I have told about the SO4 symmetry and how SO4 get reduced to SO1, 3. We have also done it. And after that, now I can say that on the last video of the topic, which will come tomorrow or something, I will prove that mod R square is dependent upon the Hamiltonian, then the series will end. I hope you have enjoyed the video. Thank you.